Now, we are going to take a look on the subtopic of inductor in an AC circuit. So, where we have only one single inductor placed within a closed circuit connected to AC generator. The output of the AC generator is this one, similar to the previous lesson. Alright, so now our aim is to measure the voltage, okay, drop within or across the inductor. Alright, so if you still remember, this inductor also the solenoid, okay. Right, inductor in an AC circuit, okay, the behavior, the way the voltage and the current behave within the circuits is displayed by this sinusoidal wave function or graph. The voltage reach its maximum value 90 degree before the current reach its maximum value. So the voltage leads the current. The keyword is before. Okay, so means that the voltage leading the current or current lags. Okay, current lags the voltage. This is actually the same statement with current lags the voltage by 90 degree. So the same statement to this, vice versa. Alright, because okay, if we refer to this diagram or graph, we have voltage first and then followed by the current. Then you can measure. So in terms of meaning and simple meaning or simple understanding, what happened actually, whenever current going to flow into the inductor going to produce its own induced voltage to produce induced B, induced I, so that it can oppose the current that flowing into it. Right? So the production of itself, the induced EMF, is measured earlier. Can be measured earlier if we put voltmeter here. Right? Compared to in terms of current. Right? So the voltmeter going to give us reading firstly. Okay? The value is reaching maximum, then the current going to be flowing into the inductor. So the effective resistance of a coil in an AC circuit is called its inductive reactance and given by this. So in simple, this is actually a measure of how big the hardness of the current phase whenever the current want to flow into the inductor. So inductive reactance is equivalent to 2 pi FL or simple omega L. Omega is angular frequency or speed or velocity. L is the inductance. Alright. And then in terms of delta V across the inductor, in terms of RMS, root mean square, right, is equivalent to, based on Ohm's law, I RMS flowing within the circuit times with the inductive reactance. Okay, the unit of the inductive reactance, okay, the unit of it is ohm, because it's a measure of hardness for the current to flow within the circuit due to the inductor. And the delta V max across the inductor is equivalent to I max times with the XL. Okay, capacity and inductive reactance. The unit of this is volt. That goes the same to this one. Right. So take a look on question number 14, page 719. However, for this question, as of now, you only be able to answer part A, B, C, D, and E. For part F, G and H, okay, please KIV first, okay. Don't answer this whenever you learn about power for RLC circuit. Alright, so take a look at this. The output of the voltage, right, of NC generator is given by this. So this one actually the V max. Get the information here. And this one is actually your omega. The generator is connected across 0.5 Henry of inductor. Okay, the unit of the inductor is Henry. Find the A frequency of the generator. So we want to solve for the frequency. So you have the information of omega. Omega equivalent to 2 pi f. So your f will be omega over 2 pi, which give you the omega is 30 pi over 2 pi. So simple is actually 15 hertz. This is the frequency of the generator. And then B, the RMS voltage. The RMS voltage, what information you have? Oh, here you have delta V max. So we are going to use this information, B delta V RMS, delta V L RMS equivalent to delta VL maximum over Z2, which give you, right, 1.2 times 10 to the power of power 2 divided by Z2, which give you 84.9 volt. Okay, then C, inductive reactance. For C, you want to determine inductive reactance. For C, inductive reactance is XL equivalent to omega L, which is the omega already given to us, 30 pi. Your L is 0.5. So you will get, okay, 47.1 ohm, right? And then D asking for RMS current. D IRMS equivalent to delta VL RMS divided by XL, which is 80, where is it just now, 84.9 divided by 47.1, which give you the answer is 1.8 ampere. And E, maximum current, E maximum current, Imax equivalent to square root 2 times IRMS, which IRMS just now 1.8. Finally, you will get your answer 2.55 ampere. Right. So now, how about if we combine them all? We combine the resistor, the inductor, and also the capacitor in series connection to AC generator. So for the AC generator, the output, the instantaneous voltage is delta V max sine, let's say, omega t. Okay, so recall back, right? Whenever current flow to to the resistor, it has no objection. Whatever comes to it, you may pass through, the current may pass through, but then the resistor going to use up some of the current, convert it into heat. All right, and the current flowing or coming from the AC generator here at any instant is I instantaneous is I max sine omega t. Okay, so how about the inductor? The inductor, the behavior of it, whenever the current try to flow into it, it's going to produce objection. The induced EMF going to be produced, and the voltage going to lead the current. Okay, within the resistor, no leading, no lagging. Okay, is in phase. However, the current voltage is in phase. However, for inductor, the voltage is leading the current by 90 degree. How about capacitor? For capacitor, okay, whenever current going to flow to it, is going to react in terms of you may flow, but before that you have to fill up the charge on my plates. So it's going to be a charging process. So the delta V cannot be measured until the capacitor fully charged. Right? So current leading the voltage. Okay, current leading the voltage by 90 degree. Alright, so based on this behavior, we can have a simple conclusion of these two. For resistor, okay, I is in phase to voltage. Right? For capacitor, memorize this one. I's. What does that mean? In capacitor, current leads the voltage. This is a symbol of EMF, right? So this is also the voltage, right? So current leads the voltage by 90 degree within capacitor. For the inductor, like this. For inductor, voltage or EMF leads the current again by 90 degree. Okay, this is a symbol of inductor. This is a symbol of capacitor. Okay, so for resistor, there is no lagging, leading because the current and the voltage or the EMF is in phase. Right? And within the capacitors, current leads the voltage, okay, by 90 degree. Within the inductor, voltage leads the current by 90 degree. Okay, so you memorize this one, inshallah it will be easier for you. Right, whenever you want to sum the delta V, okay, because there are connection in series, isn't it? If you put you make a sum of delta VR plus delta VL plus delta VC, is not equals to the delta V here, because the behavior for each of them are different. Okay, so sometimes whenever you add up like that, straight up like that, you might get the value of it bigger than delta V max. Sometimes you will get the value of them equivalent to 0. So it means that this is not logic. So you cannot have delta VR plus delta VL plus delta VC just like that or simple like that. It must be somehow with reference to the behavior of them. What madam means is this one. Okay, so based on this, you see this is a current flowing within the circuit, okay, origin from the AC generator here. This is the behavior of the resistor. The delta VR, okay, is in phase to the current. But then for the inductor, what was that just now? I's LE. So for the inductor, this one inductor, okay, voltage leads the current because if you see here it's cos, this one sin, so it's leading by how many degree or radian? Leads by 90 degree. Okay, so within the capacitor, the story is different. Okay, where the current right now leading the voltage. So the current leading the voltage is sine function. This one is negative cos, isn't it? So if you want to have a sine function as well, so this is the sine function. So it start later. The voltage, okay, start later. Okay, lags behind. Okay, or the current is leading by 90 degree. So at any instant, okay, to have the summation of the delta V across the three elements here, you have to consider each of the behavior, so each of the value, and then you have to have this kind of summation of, this is actually summation of or resultant, right? Kind of very hard for us. We are not going to waste our time to take a look and add up one by one point to another point. So it's taking a very long time. It's kind of difficult. All right. So we have an alternative method. We call it phasor diagram. This is actually a method. Okay, a mathematical method where we are using vector technique. Okay, we are using vector technique to account, okay, for the different phase of the voltage drop within resistor, capacitor and inductor. This is a vector technique, represent the voltage across each element as a rotating vector called a phasor. Why is it rotating vector? Because rotation can be converted into vibration or sinusoidal wave function. Remember our function just now is sin, is cos. Okay, so the diagram is called a phasor diagram, where, okay, basically, okay, for a complete circuit, just similar to our previous page just now, we have a delta V max, okay, a delta V at any instant, and this phasor diagram is rotating counterclockwise direction as standard. And phi here is the phase angle. Okay, phase angle. Okay, what is phase angle? How big the difference, how big the delay is, or lagging behind or leading in front, right? So it's considered with that to the respect of, normally to the respect of current, right? Because current is our reference, right? So next one, for each of the elements that we used just now, inductor, capacitor, okay, and resistor, this is the behavior of the voltage, because based on the reference of current here. For the for the resistor, okay, it has no lagging or leading, it's in phase. So the delta VR and the I is in phase. That is why we represent the phasor for them, okay, like this, right? However, if we recall, for the capacitor, the current, okay, leading the voltage. So the current is leading the voltage. So the current leading the voltage. The current is here. For the current to be in front and the voltage to be later, okay, at the back. So this is the arrangement, whereby your delta V across capacitor now is pointing to the negative y-axis. The angle between them is 90 degree. So next one will be inductor. For inductor, voltage leads the current. If the current already on the x-axis, so means that the voltage across the inductor must be pointing to the positive y, because it's leading before, and the rotating must be counterclockwise, rotating with the omega of angular frequency. So again, the angle between the delta VL and the current is actually 90 degree, similar to the analogy or the graph just now. Alright, so since this is a vector, this one can be rearranged, right? We can rearrange the position of the arrow, because the arrow is representing a vector, right? So you have here delta VR of the resistor, delta V across the resistor. Here you have delta VL, so delta VL along or pointing to positive y-axis. Delta VC is pointing to the negative y-axis. Therefore, we can have a resultant between delta VL and delta VC. So here is the resultant. Here is the resultant between these two, delta VC and delta VL. That is why, okay, they put it as delta VL minus delta VC. Why is it minus? This is actually delta VL plus negative of delta VC, because it's pointing downward. Okay, we are figuring out the resultant along y component. So from these two, just now you have delta VR, then you have delta VL minus delta VC, right? So by using tail to tip method, from this, the tail of the first vector to the tip of the second vector, this is your resultant, which is also your delta V max. Okay, the angle here is your phase angle of phi, right? With reference that we have here current, or in other word x-axis, in other word here y-axis. Okay, so this is a vector technique. So again, all over again, you're going to have the hypotenuse, okay, to have the magnitude of the delta V max. You're going to calculate, okay, the hypotenuse. You're going to calculate tangent theta, tangent phi in this case, right, all over again. So just like a vector technique. Okay, so this is what I'm talking about just now. Okay, here is to find the magnitude of your delta V max, right? So you are using theorem Pythagoras, okay, and then to have the direction tangent phi equivalent to delta VL minus delta VC over delta VR. What is this actually? This is actually in comparison, yeah, this one is square root of V max, delta V max in terms of x square plus delta V max component y square, isn't it? So here is your actually delta V max y component over delta V max x component, right? So that is how we know it's supposed to be tangent, okay, because to the respect of this angle, this is actually opposite side, this is adjacent side. That is why it's tangent phi. Okay, so phi here, this is actually phi. Phi is the phase angle between the current and the maximum voltage, right? So where is the current? By the way, the current lies along delta VR. How we know? Because current and delta VR is in phase. Alright? So the angle here is measured from delta V max to the I, the current. So based on that, when we combine the three elements there, okay, all together in series to a generator within a complete circuit, each of the element going to have their own behavior, right? The resistor, okay, you may come, I'm going to use you up. Okay, the inductor, no, I'm going to produce my own, I don't want to change. The capacitor, you may enter, but then fill up my plates firstly. So the behavior for each of the element here, okay, impedes the way current flow within the circuit. Impedes, or here we call it as a kind of reaction, or we call it as impedance. Okay, impedance in simple is also a kind of R equivalent. Okay, similar analogy to R equivalent in a DC circuit. Okay, so to have, based on Ohm's law, okay, delta V equivalent to IR. So for this case, delta V equivalent to I Z. Okay, for a complete circuit. So the Z is, we call it impedance of a circuit. It's a combination between R, XL and XC. Why is it the formula XL minus XC? This is actually because of the phasor diagram technique just now. Similar approach to the previous slide. Okay, so based on this, okay, delta V max, right, if we open up this one, okay, Z itself is delta V over I. Okay, delta V just now, delta V equivalent to delta V max, yeah, delta VR square plus delta V L minus delta VC square root everything, right, magnitude of it. So it's I max square root of I max R plus I max XL minus I max XC, everything square root of everything. So if you see here, we can have a Z equivalent to R square plus XL minus XC square. That is how we get this equation. Okay, in terms of phasor diagram, it can be sketched like this, right? And the angle here again like this, to the respect of between I and the V max, because the I is here. Okay, also here is x-axis and here is y-axis. Okay, because we are using tangent, phi, so we are actually taking opposite side over the adjacent side, right? So the unit of the Z, what was that? Must be in ohm. The unit of the Z is actually ohm. The unit of the Z is actually ohm, because it's just a total of the impedance, okay, coming from the R, the XL and XC. Okay, impedance and Ohm's law. Okay, so if we're talking about Ohm's law, delta V equivalent to IR. Okay, initially delta V equivalent to IR. This is the common one that we used to. If we're talking about delta V max in AC circuit, so you have I max Z. Okay. Or if you're talking about delta V RMS of the circuit, I RMS Z. Okay, this is what does that mean by impedance and Ohm's law. Okay, next one, summary of circuit elements, impedance and phase angle. So the symbol like this is resistor, the impedance of it, the phase angle 0 because it is in phase, there is no phase angle. For capacitor, the impedance symbol is XC. Okay, the phase angle negative 90 degree. Why is that so? Because it's I's formula, if you still remember. So means within the capacitor, the voltage, okay, is lagging behind. The voltage lagging behind. That is why negative here. Okay, lags behind. The voltage is lagging behind. For inductor, XL, it's positive. Why is it positive? Because LE. Right? Because the voltage, the EMF, is leading by 90 degree. Leading the current by 90 degree. If you only have two, okay, resistor and capacitor, means that your Z will be this one. This kind of, because by right, okay, originally Z is equivalent to square root of R square plus XL minus XC square. So if you only have R and L, so what happened? There is no XC. This one becomes 0, right? That is why your formula become this one. Okay. If let's say you only have XC, no XL, this one becomes 0. So negative of XC square, you're going to get positive value, right? How about you have all of them? So this is the things like this one, right? So in terms of phase angle, okay, if you have negative between negative 90 to 0, if it is positive, it's positive 0 between 0 to 90 degree. If you have all of them, the three elements combined together, then if your phase angle, the phi, if the phase angle you have negative value of it, negative 5 degree, let's say, okay, it means that XC is bigger than XL. Why is it so? Because this one is bigger. Okay, this one is bigger. So you will get your answer negative. Okay. If you get your answer is positive, it means that XC is less than. Or in other words, XL is bigger. XL is bigger, it means positive. Okay. The range, it depends on the value of the XL and the XC.